A grid-tied inverter is a device that you can use to put power from a DC source, like let's say solar panels or batteries, wind turbines, into an AC power grid. Now, a while back I made one of these things myself, and while it worked, it was quite terrible. It had really bad performance, low efficiency, really bad power factor, about 0.5 I believe. It also produced a lot of noise, both actual like audible noise and electromagnetic noise, as pointed out by one of the comments as well. So it's about time we do this again, but this time a little bit better. And so that's what today's video is all about. So this is what the new power inverter actually looks like, and although it might not look like much, let me tell you that it is actually a massive improvement over the previous version, which you'll see in a moment. But first of all, let's take a look at how this thing actually works. So the core component of any power inverter is of course an H-bridge. So an H-bridge is a circuit that consists of 4 switching devices, usually some type of transistors, MOSFETs or whatever. And what it can do is you can use this to send an electric current through a load in 2 directions. And so this is what you need to turn DC power into AC power. Now, while it is possible to build your own H-bridge from scratch, it is of course much easier to take an off-the-shelf H-bridge. So that's exactly what I did, and that's where this module comes in. So this device is called the IBT2, and it is a motor driving module that you can use with an Arduino or any other microcontroller, of course. And what it is typically used for is driving DC motors. So you can use it to spin a motor in 2 directions. But of course, if you just switch that direction back and forth really fast, essentially it's just an inverter, right? And this is just an H-bridge circuit in a package. And what's so nice about this module is that it's a completely functional H-bridge that you can drive directly with an Arduino or any other microcontroller that you like. And so you don't need to worry about designing the circuitry, driving the MOSFETs, bootstrapping, shoot-through protection, all that kind of stuff. It's all taken care of. It's quite brilliant. Now, what's also good about it is that it can handle quite a bit of current. It claims up to 40 amps. I'm not sure it'll do 40 amps continuous. Maybe 20 would be a more realistic number, but at least plenty of current for what we need it to do. And it's also reasonably cheap. I think I bought it for like 10 euros. Now, should you attempt to do something like this yourself, and you want to use this module, there are a couple of things about it that I think are important to know. So I'm going to put those in a small text document that you can find, along with all the schematics and code for this entire project, and there'll be a link in the video description. So then, to drive this H-bridge, I'm just using a super basic Arduino Uno microcontroller, but of course this could be any other microcontroller that you like, but I had this Arduino laying around, so I simply used that. Now, the next thing we need to do is we need to use that H-bridge to generate a nice AC sine wave. And to do this, we're going to use a technique called SPWM, which means that you essentially generate a sequence of very, very short pulses whose length varies based on the amplitude of the sine wave that you want to create. And then if you take that output, which is still quite ugly, and you feed it through a low-pass filter, you can then smooth that out into a nice-looking sine wave. So in my case, I'm doing SPWM at a frequency of about 10 kilohertz, about 10,000 of these short pulses per second. I then send that through a low-pass filter, which consists of a 100 microhenry coil combined with a 35 microfarad capacitor, and that then gets smoothed out into a pretty nice-looking sine wave that looks like this. Now, you could get an even cleaner output if you used an even bigger coil and bigger capacitor, but I figured this would be good enough for what we're trying to do here. I've also installed a potentiometer on the inverter board, and by turning that potentiometer you can vary the maximum duty cycle of that SPWM sequence, so that varies the amplitude of the output. Now then, that nice clean sine wave is fed into a transformer which transforms it from about 15 volts AC up to the 230 to 240 volt AC that we're going to need to feed this into the power grid. So now that we've successfully built a power inverter that works, the next thing we need to take care of is synchronizing this thing to the power grid, because as we've discussed before in those previous videos, it is absolutely essential that a grid-tied power inverter, as the name suggests, is perfectly synchronized with the power grid. So how do we do this? Well, the first thing we need to do is there needs to be a way for this controller to monitor the grid's voltage, or at least monitor the voltage on the AC side of things. So we're going to connect it to the low voltage side of our transformer. So what I've done is I've made a little network of resistors that I've soldered onto a small piece of prototype board that essentially just lowers the voltage down to a level that the Arduino can handle. So I believe the peak voltage is now about 3 volts or so. Also, the diodes in the H-bridge module act like a rectifier so that the Arduino doesn't get exposed to negative voltages. So if you then look at the voltage that the Arduino sees, it looks something like this. So it only sees those positive halves of the sine wave that is produced by the grid. So what it then does when you turn it on, the Arduino is going to wait for this moment right here, which is what we call a zero crossing. And exactly on that moment, it's going to start producing its own PWM-produced sine wave that we just talked about, and it's going to produce exactly 1 cycle of that sine wave. So let's just draw that in here, shall we? So the dotted line is essentially the output produced by the inverter. Now if all goes exactly to plan, then of course the cycle time, or the period time that our inverter produces, is exactly the same as the period time of the grid, so they're perfectly synchronized, and so it's going to land exactly on the next zero crossing, and then once again we can repeat the same process. But of course in practice that's not always going to be the case. It's possible that the period time is a little bit too short or a little bit too long. So let's say that our period time is a little bit too long, so we actually land a little bit too late, say right there. So what the Arduino then does at this moment is it takes a measurement of the voltage, and it's going to notice that the voltage is now positive, and that tells it that apparently we were a little bit too late, right? Our period time was too long, we landed past the zero crossing, and so the next cycle will need to be a little bit shorter to compensate for this. And so that's what it does. So when it reads a positive voltage, it'll reduce the period time a bit and then produce the next cycle. The opposite is also true, right? It's possible that our period time is actually going to be a little bit too short. So we land a little bit early, we actually end up landing before the zero crossing. Now that's a bit more tricky because there is no way for the Arduino to know if we've landed exactly in the right spot or too early, right? In both cases it's going to read 0 because it can't see negative values. So either way, if we read 0 volts, it's going to lengthen the period time by a little bit. So if we're a little bit early, it's going to lengthen it and everything will be fine the next cycle. Perfect. But if it's already right in time, so let's say we've already landed exactly where we need to be, it's also going to lengthen it a tiny bit. But that's not too big of a problem, right? Because first of all, it's only a tiny little bit, right? What I've been drawing here is already an exaggeration. In reality, the steps that we're talking about are much smaller than this. And also, if we make it a little bit too long, then that's simply going to get corrected for the next few cycles. So that way, every single cycle, it keeps making a small adjustment to keep the inverter's output perfectly in phase with the grid voltage. And that is how the inverter stays synchronized with the grid. Alright, so we've got our grid-tied inverter over here, which is plugged into a small DC power supply, which is being powered by this LiPo battery over here. So that is our power source for today's test. Then on the AC side of things, I've plugged in this little power monitoring device over here. So at the moment you can see that it tells us the grid voltage is 232 volts and the frequency is 50 Hertz, as it's supposed to be, of course. And if we set this over to power mode, it'll tell us that we're using 0 watts of power, because obviously nothing's plugged into it at this point. Now, I've verified that this device is actually accurate by comparing it to the numbers from the official utility supplied electricity meter that is in the house, and it turns out that this thing is pretty much spot on, which is good news for this test, of course. However, one thing that's a bit weird about it is that it doesn't tell you which way the power is going, so it doesn't have like a positive or a negative sign on the display here. So if it says 50 watts, you don't know if that's 50 watts being consumed or 50 watts being pushed back into the grid. So when I turn on this inverter, you'll just have to take my word for it that the power is actually going the right way. Okay, so let's just go back to our inverter over here. Start by turning on the power supply, like this, so it's at 24.5 volts. Then we also need to plug in this USB cable to power the Arduino. There you go. And right away you can see that this orange LED over here turns on, which means the inverter is now in standby mode. So it's not doing anything yet, right? It's not producing any output voltage whatsoever. So if I take the power cord that is connected to the output of the inverter, I can safely touch these pins. I don't feel a thing, because the inverter will not turn on until you actually plug it into the grid. So now let's take this power cord and plug it into our monitoring device, like this. And then we're going to turn on the inverter by pressing this button right here. There you go. So the inverter is now running, which is indicated by the green LED, which is now turned on. So if we go back to our power meter for a second here, you'll be able to see that we are delivering about 82 watts of power to the grid at the moment. So let me just turn that potentiometer, see if we can put some more power. There we go, 100 watts, 130, 140, come on. That's about the most it'll do, about 143-ish. So you could probably get more power if I were to increase the DC voltage of the power supply a bit further. And the electronics would probably handle it just fine, because it's all running pretty cool. Right? These things could probably handle far more power than this. However, my transformer is only rated to handle 10 amps of current, and I'm pretty sure that I'm already exceeding that number on the transformer coil, and I don't really want to burn up the windings in this thing. So that's about as far as I want to push it for now. So it's not a particularly powerful inverter, especially given how bulky it is. Mainly because it's limited by the capabilities of this transformer. But it still is quite a bit more powerful than the previous grid-tied inverter, which could only produce about 70 or 80 watts or so. Now, speaking of the previous grid-tied inverter, this thing is actually a massive improvement. First of all, because of course it produces this pure sine wave, so it's producing way less noise, but also the efficiency is much better, and quite notably, the power factor is much better. So if we look at our power monitor again over here, what you can actually see is that we have a power factor. We're delivering about 100 watts at this point, and the power factor is about 95. So that's actually very close to 100%, whereas the previous version, if you remember, had an efficiency, or sorry, a power factor of about 50 or even less. So that is a massive improvement, really. Also, the efficiency of the inverter is not that bad, so we're producing about 102 watts of power. And if we look at the DC power supply over here, you can see that we're using about 138 to 140 watts or so. So that means I think the efficiency is around 75%-ish. And of course that changes a little bit depending on the conditions, right? Depending on the load, the duty cycle, the grid voltage. I think the best I've seen this thing do is about 80%, so that's pretty much peak efficiency of what you can do with this. Which is, you know, not fantastic, but it's also, I think it's not bad for a homemade device like this. Now, something that is quite important in the world of grid-tied inverters is error detection, particularly when it comes to frequency. So the power grid is designed to operate at a very specific frequency. Here in Europe, that is 50 Hz. That frequency can vary a little bit, so typically between 49.5 and 50.5 Hz, but you can see that the range is quite small. And if it goes outside of the range 49 to 51 Hz, there is probably something seriously wrong going on, and power generators and inverters fall under that category too, need to shut down as quickly as possible to prevent damage. So what we need to do as well is in that code that runs on the Arduino, there's a couple of lines that check if the period time, and therefore the frequency, is within a certain range. And if it's outside of that range, the inverter will actually turn off and go into standby mode. Now, earlier on in the video, we talked about how the inverter makes a small adjustment to the period time, and therefore to the frequency, every single cycle of that AC sine wave. And that makes it sort of inherently unstable. If the grid voltage isn't there, or the grid voltage doesn't have a nice consistent frequency, then what is going to happen is the output frequency of our inverter is going to drift, and so it's going to go out of range, and the inverter will turn itself off. And to demonstrate this, what I've got here is a power strip which has this fan plugged into it over here, and my soldering iron, which is over here. And now, full disclosure, for those of you wondering, you know, why is the power cord here a different color than the power cord going into the fan? Well, because this is sort of a Frankenstein contraption here. You can see it is actually the same cable, so don't worry about that. So what I'm going to do now, oh, by the way, the inverter is also plugged into the same power strip. What I'm going to do now is I'm going to plug this power strip into the outlet. So here we go. We just take that, we plug it into the power meter. There we go. And you can see that we're using about 98 watts of power right there. Okay, and so you can see the fan is spinning and the soldering iron is warming up there. And so now what we're going to do is we're going to turn on the inverter, just like this. There you go, so the inverter comes online, and now what I'm going to do is I'm going to turn this potentiometer to try and precisely match the power consumption of the soldering iron and the fan. So we just look at the meter over here, like this. So we're now at 19 watts. I'm just going to increase that a little bit. 7, 6, 2. It's pretty difficult to get it exactly to 0, but there you go. So we're using pretty much no power. It's almost at 0, right? So that means there is basically no power flowing through this cable. There is no power being used from the grid, and there is also no power being put back into the grid. It's just the inverter powering the soldering iron, powering the fan. However, the grid is still connected to it through this cable, right? It's still synchronized with the grid. So let's see what happens if we unplug that cable, right? So there we go. We just pull this whole thing out, and straight away you can see the fan stops spinning, the power turns off, the inverter goes into standby mode. So when I unplug that cable, the frequency becomes unstable, it goes out of bounds, and the inverter turns itself off. And it's supposed to do that, right? It's supposed to do that because power inverters like this need to be deactivated during a power outage, because you don't want these things back-feeding power into the grid, because there might be people working on those cables. They might assume that the cables are, you know, that these power lines are dead. So you don't want a bunch of inverters at people's houses back-feeding power into those lines during an outage. So it's very important that this happens. There is a bunch of things about this inverter that I would still improve, because yes, it is an awful lot better than the previous version, but there are still a bunch of things about it that I would like to change. First of all, the microcontroller needs its own power supply. So right now I'm just running the little Arduino from my laptop. I'm just powering it through the USB port. I need to put some sort of 5-volt regulator on there, or a little DC converter, so that it can power itself without being plugged in all the time. That would be quite nice. Another thing that I want to do is I'd want to add a voltage and current probe to the output, so to the high voltage side, that can be read by the Arduino, so that the Arduino actually knows the real grid voltage and the real current that it's delivering into the grid. The reason this is useful is because it would allow you to implement power control or current control rather than amplitude control. Instead of having the potentiometer being tied to the amplitude, it would be tied to a certain amount of power. So you'd set it to, let's say, 100 watts, and then the Arduino could adjust the duty cycle or the amplitude dynamically to always get exactly 100 watts. So you could get the same amount of power regardless of what happens to the grid voltage, which would be a lot better than what it's doing right now. So that is something I think I'm also going to implement on this thing. I'm just looking for the most effective way of getting, or like probing, the high voltage side with the Arduino. I suppose it's going to be some sort of optocoupler based solution or something along those lines. I haven't really given that much thought yet. Right, so that is the homemade power inverter, the homemade grid-tied power inverter version 2. I really hope you've enjoyed watching this video. If you did, maybe click the like button or even consider subscribing to this channel. And all that's left for me is, of course, to say thank you for watching.